Did absolutely great with that. So now that we're all enthusiastic and ready to go, we're using our calculator. Now, let's make sure we're all kind of looking at the same thing. And let's talk about what our approach might be. So the way this problem is set up, we could graph this as one equation and this as another equation. Would you agree with that? And if we did that, we'd have two different equations going, two different curves going, and we would be looking where they crossed each other. Okay, so that's one strategy. You could also move everything to one side, get it set equal to 0, and then look for where it crosses the x-axis, right? Both of those are options. I think since it's written this way, I'm just going to leave it like this. So I'm going to go to zoom 6 and make sure I have a standard window. That's how I'm going to start it anyhow. I'm going to clear out all the old equations that I have in there. Now, when I type this in, do you all know where your square root button is? Okay, so when you square root, up will come a parentheses. So you're just going to type in your x plus 6. And then I'm going to type this in as y2. Do they look like they cross each other? All right, let's find it. So second calc intercept. Remember, your answer is going to be the x coordinate. You're solving for x. What did you get? 2.66. About 2.66 if we round off to the nearest hundred. Any question about that? And everybody understands you could have moved everything to one side and found the x-intercept. All right, try the next one on your own. Any way you want to do it. So whether you want to use second calc intercept or second calc 0, whichever way you want to do it, go ahead and do it and see what happens. Here's what I got. I don't know if those are right. So they match those? Yes. So we're all good? Now, this one would have been a bear to solve without a calculator. But this one you could have solved easily without a calculator because what kind of equation is this? Quadratic, yes. So you're going to move everything over and then use the quadratic formula maybe. And that those are the answers you would have come up with. Perfect. 1.1, due on Thursday. Mark your calendar. Now we're on to 1.2. We're going to talk a little bit about functions and function vocabulary. Oh, this is big stuff. Yep, functions and function vocabulary. All right, so here we go. First of all, what am I talking about when I say a function? I throw that word out like it's nothing, but it's really a big deal. What is a function? No, that's continuity. That talks about how a function can be continuous. What is just a plain function? What do I mean by the word function? No one knows? It's a, Kara?
How like things react to each other, like if you change one thing and then other thing?
Okay, so a function is thought of as an input-output machine. You input it in, it gets changed around, and something else comes out. Absolutely. A function is a set of ordered pairs where none of the x's repeat. So you remember the old vertical line test? That's the test for a function. No x's repeat. It is a relation, a set of ordered pairs, where every x has just one y paired with it. Does that sound at all familiar? That's a kind of a big deal. Yeah, functions are a big deal. All right, so now we're talking about some specific characteristics of functions. And one of the words is continuous. Now, I'm going to be real honest with you guys. The definition of continuity is right there. The limit as x approaches a of f of x is equal to f of a. You're like, what is she even talking about? So I'm going to tell you kind of a real person, not mathematics, but the real person definition of continuity. A function is continuous if you can draw it without lifting your pencil. If you can draw it without lifting your pencil, it's continuous. So, an example of a continuous function, and there are zillions of them, but this would be continuous because I can draw the whole thing without lifting my pencil. That means that the limit as x approaches a of this function is f of a, but that's the formal definition. Basically, I can draw it without lifting my pencil. Now, functions can be discontinuous in a couple of different ways. One of the ways is that they have what's called a removable discontinuity. A removable discontinuity is otherwise known as a hole in the picture. So, for example, I could draw a shape like this. That is what we call a removable discontinuity. And you'll understand what that means when we start graphing these things. But for now, your definition is it's a hole in the picture. Notice I drew two little grids there because you can have this or you can sometimes have this. The original shape doesn't matter. So you can either have no point at all defined here, or you can have a point defined there, but it's not part of the curve. These are both considered removable discontinuities. Now, are they both functions? Yes. Some people think this one's not a function, but it is because that's an open point. So when I draw that vertical line down through, don't I hit just one place? Yeah, this is a function. So removable discontinuity, or a hole in the picture, can show up as either just a hole or a hole with the point placed somewhere else. Then you have jump discontinuities. Do you remember graphing, you probably called them step functions last year. Does that sound familiar, a step function? Or does it look familiar? No? Okay, well, do you understand why that might be called a step function? And it's also got jump discontinuity. Certainly, I cannot draw this without lifting my pencil. And when I lift my pencil, I'm jumping up a step. So this is called a jump discontinuity. So far, we can be continuous, We can be discontinuous because of a hole, literally a hole in my picture. Or we can do this jumping around stuff. The most serious discontinuity is the non-removable or the infinite discontinuity. And it is graphed as an asymptote. So asymptotes are non-removable or infinite. Both of those, know both of those words, I don't care which one you use. But a non-removable or infinite discontinuity is an asymptote. These are the most serious in terms of causing us problems. In an ideal world, our functions are all continuous, but that's not the case. So we gotta learn how to deal with all these things. Okay? All right. So that's kind of definition stuff, memorize that. Now we're gonna actually do a problem that involves not just continuity, but other function vocabulary as well. Now I want you need to be able to graph this thing without a calculator, but I want to show you how, just so you know, if you're ever in a pinch. We're going to graph this on our calculator, so go to y equals, like you always do. Clear out the old. Okay, now, the absolute value, have we talked about this already? The absolute value feature is located in your math menu. So right here is a button called math. And then once you press math, you see a bunch of options across the top. Go over to number, the second one, NUM, and the very first option is absolute value. So you press enter, and then type in your x plus 2, close the parentheses, and subtract your 1, and hit graph. Did you expect that? Did you remember that at all from last year? Because I know you graphed these last year. The V shape, absolute value V's, that's how we remember absolute values are V's. And this V is vertexed where? Where is the actual V point of it? Can you tell? At -2, -1. Because adding 2 inside the grouping, inside the absolute value or the parentheses, whatever you've got here, moves you left 2. And then this number, which is outside the grouping, moves you down 1. Yep. So we've got our handy dandy V, which you need to be able to sketch that without a calculator, but I wanted you to know how to get that on your calculator if you needed it. Okay, so let's answer some questions. Continuous.
Yes.
Yes, indeed, that's continuous. So I'm going to say it once again because this may be the first time you ever used that word. And it's kind of an important math word. If you draw it from left to right, everything moves left to right. If you draw it from left to right, you do not need to lift your pencil. That makes it continuous. Okay? If it had a break in it somewhere and you had to lift your pencil, then it would not be continuous, but this one is. Yes. All right, increasing versus decreasing. Some functions are all of one, and some functions are kind of split between them, but again, we're moving left to right. So what happens in this picture, as I started, I am going down. So I am decreasing from -infinity until I get to what? I'm moving left and right. So until I get to -2, I'm decreasing. Remember, I'm moving left to right. So I know that arrow goes up, but I'm going this way, left to right. So I'm going down, 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 down until I get to -2. I'm moving left to right, so I'm looking at the x's. And then what happens once I get to -2? Now I'm increasing. This is like your pivot point right here. You're decreasing till we get to -2, and then we are increasing after that. Bounded above, below, or bounded. You want to take a wild guess about this picture? Do you think it's bounded above, below, or both? This means both. This means you're bounded above and below. So any guesses about that picture?
Above.
Bounded above?
Yep.
I got a vote for bounded above. You're voting for that too? Don't buy a lottery ticket. No, we're not bounded above. Bounded above means it has a ceiling. Does this picture have a ceiling? Is there anything stopping it as it goes up? No. So it is not bounded above, and therefore it isn't bounded, because to be bounded means you're bounded above and below. And if I'm not bounded above, then I'm not bounded. I am, however, bounded below. Does there appear to be a floor to this picture? A point beyond which we do not go any lower? Yes. So we are bounded below at not y equals 0, y equals -1. Our lower bound, this is called a lower bound, is -1. Up and down, lowest point is -1. You okay with that? Okay. Remember, this word means that you have an answer here and an answer here. We may have a picture like that soon.
So we use the y value because it's going
Up and down,
and then for increasing and decreasing.
left and right.
Okay.
Whatever direction you're going, as you analyze the picture, that's the letter you use. Okay? Good question. All right, asymptotes. Does this picture have any lines that the curve approaches but doesn't intersect?
Y equals -1.
That is not an asymptote. Remember, if it's it's a lower bound, but it's not an asymptote. Remember, if it's an asymptote, then the curve does something like this,
Oh, right.
approaches it. And we do not have that in this case. Asymptotes are lines that the curve approaches but doesn't intersect. These are asymptotes. These are supposed to be dashed lines. These would be asymptotes. See how the curve gets closer to it as it goes out? So we have no asymptotes. No asymptotes on this one. Maximum, minimum. Maximum, minimum. Okay, take a look at your picture. That's this one right here. Does it appear to have a maximum, Katie? No, there's no maximum. What does maximum mean? Highest point? Do we have one? No, there's no maximum. However, does it have a minimum? Its minimum, okay, so no max, and its minimum is the point -2, -1. Now, not pertinent in this problem, but I want to share something with you. Suppose we had a picture that looked like this. So we have this point, let's say that's -1, -1, and this is 2, 1. These 2 points are both considered minimums. They're what we call relative or local minimums. And what that means is, this point right here, compared to the points on either side of it, that's the lowest point. Same with this one. Compared to the points on either side of it, that's the lowest point. So both of those are considered local or relative minimums. This guy is called the absolute minimum because why? He is the very lowest point. So we have two kinds of minimums and maximums. We have relative or local, and there can be multiples of those. And then we have one absolute minimum. So when I look at this picture, this is a relative minimum, but it is also the absolute minimum because it is the lowest point on the picture. It's the only minimum we have in there. All right, symmetry. Does this thing have any symmetry? Yes, Robbie, it does. Can you tell me about what? What is it symmetric about?
Both sides, like left and right.
Okay, about this line right here?
Yeah, so -2.
In geometry or algebra or sometime, you probably called that the line of symmetry or the axis of symmetry. And he is right. It is the line where x equals -2. So it has symmetry about that. Remember, symmetry means if you folded these together, they would be right on top of each other, right? Identical left and right of that line. Nicely done, Robbie, good. Okay, a couple more and then we're done with this. Domain, range, and zeros. All right, let's look at our picture. Let's look at our picture. Tell me about the domain. What do you think the domain of this picture is? Katie. Bingo. Average guy on the street is going to say all real numbers, right? Everything. This thing goes forever left and right, nothing stopping it, so negative infinity to infinity, very good. Now, what about the range? Kara?
Is it -1 infinity?
-1 to infinity. Do you think she's right?
Yep.
Absolutely. -1 up is your range. Beautiful. Zeros. We graphed this on our calculator. Could we find the zeros, otherwise known as the x-intercepts? Second calc 0. So we can do it on our calculator. Can we do it without our calculator? Yes, how? Yeah, we don't plug in 0. We set it equal to 0. And then somehow you solve this equation. You know, I'm gonna do it on a number line. Some of you are gonna split that up into two different equations, x plus 2 equals 1, x plus 2 equals -1. Either way, the zeros are at -3 and -1. The zeros are these points right here where we cross the x-axis. And you can find those either on your calculator or by setting your equation equal to 0 and solving it. Okay. Mm-hmm.
So why do we change the 1 to a negative and not the x plus 2 to x minus 2?
What are you talking about?
With the zeros, because we set it to 0, equal to 0, right? And then to get -3, we made the 1 a negative. Oh, because we did, okay.
1 unit on either side. All right, so here's what I want to do. I want to take about, 2 or 3 or 4 minutes. And I want you to repeat all the exact same questions with this new equation, y equals 3 minus x squared. Before you start, let's see if we can graph this. Now, your calculator. Is that right? Is that period over?
Yeah.
Oh my God! right, well, we'll pick up here tomorrow. It does. Don't you be making fun of me. We had a ball and you know it. And that's where we're gonna start tomorrow. All right, good work, folks. Man, that went fast. I can't even